speaker. And for those at the back, there are some seats at the front, so feel free to trickle down.
Try to get through this without blowing everybody's ears out. It's my honor to be here today to introduce this afternoon's keynote speaker, Dr. Talia Travisaru. What's her name? Talia is my former coworker, and she's the current technical director for Fugro's land division in the Americas and the practice lead of Fugro's global earthquake engineering group, located in Walnut Creek, California, just east of San Francisco. I first met Talia either on my first or second day at Fugro in 2007. I had been hired as an engineer in the onshore geotechnics group, and Talia worked a few floors below me in the earthquake engineering group, who was led by their manager, Jacob Chalco. When my CV circulated the office, Jacob had noticed that I had some experience in centrifuge modeling, which was the basis of my master's thesis. After this, I was quickly whisked away to a secondment in the earthquake group to lend a hand with a new and exciting project, which ended up being the centrifuge model test for the BART Transbay tube seismic retrofit, which runs beneath San Francisco Bay. Over the next 6 months or so, Talia and I spent countless hours, days, nights, sometimes weekends, planning, building, and testing scaled centrifuge models of the Transbay BART tube at the UC Davis Center for Geotechnical Modeling. It was a learning experience for us both, but I enjoyed watching a numerical modeler like Talia, excited to get her hands dirty and learn the techniques that us physical modelers use to assess a problem, and eventually witnessing her enthusiasm when the model tests were successful in achieving their goals. Working with the earthquake group, I quickly came to realize how brilliant an engineer their manager Jacob was, and working closely with Talia, I came to learn that he also had an incredible ability to identify other brilliant people to work with him and mentor to become leaders on their own. Talia brings to us her over 20 years of experience that she has gained following the completion of her PhD at UC Berkeley under Dr. Jonathan Bray. Most of us in this room have no problem recognizing these two names put together, Bray, Travisaru. In those years, Talia has grown what I knew as a relatively small, locally focused Northern California earthquake group to a globally recognized practice area within Fugro, all the while leading projects across the globe, such as the aforementioned BART Transbay tube retrofit, the Port of San Francisco Seawall Resiliency Program, the new Samuel de Champlain Bridge in Montreal, Panama Metro Line 1 in Panama City, and the Osman Ghazi Bridge over the Gulf of Izmit in Turkey. Closer to home, Talia lends her time to advising the San Francisco Bay Conservation and Development Commission to ensure that planned projects within the bay margins are resilient and are afforded adequate protection from geotechnical hazards. Once again, it's my pleasure to welcome my friend and former colleague, Dr. Talia Travisaru, to give us her keynote lecture.
Hi, hello, good afternoon. I'm extremely excited to be here. I was here back about 3 months ago to attend the earthquake conference in the Canadian Earthquake Conference, and I realized at the time that the level of presentations was very high quality. I was really impressed. So I'm very honored to present to this audience of seasoned engineers, and thank you very much to the organizing committee for inviting me. I was not expecting this introduction. I really appreciate it. I feel humbled. They asked me to send me my CV, as this is a sort of more standard, right? So that Stephen can introduce me. And what he said is completely, I sent him my CV, and he made such a warm introduction out of this. So I'm also going to say that I very fondly remember those days that we were working together on BART. When you go to my office in Fugro, I only have one framed picture on the wall. It's not my family, it's not my PhD degree or another diploma. It's essentially the picture of the team on the centrifuge test, and you're on it. So I appreciate the introduction, but let's get to the talk. So it's after lunch, and it's a long topic. So let's see if I can do justice. So I would like to talk to you about geotechnical best practices for risk-informed decision-making in earthquake infrastructure design. And This is a topic that I really spent some time thinking about. What am I going to present to you? I had a pool of interesting projects, but I didn't want to just present a project. So distill some lessons learned and put them under a framework. So it appears long and confusing, but hopefully I'm going to. The presentation hopefully is going to be self-explanatory. And I will welcome your questions at the end. So let's start. You're probably aware that the vast majority of infrastructure projects underperform, that is, exceed their original budgets and schedules. And there are some studies pointing to this. To the left, you see a study by Flyberg suggesting that on average, we have cost overruns on infrastructure projects by about 30%. And this is based on a study of about 250 projects around the world. To the right, you see a study by McKinsey looking at schedules, when we see that now this is mega projects, not just infrastructure, but very large complex projects, that they exceed on average their schedules by about 40%. And so it appears that indeed, infrastructure projects experience, it's quite common to experience cost and budget overruns. And in fact, it is geotechnical issues that contribute to project risks and to problems during constructions which result to claims. So this study by Clayton identifies specifically soil boundaries, soil properties, site investigation as the key factors creating problems during construction. And this audience of geotechnical engineers will not be surprised by such a graph that I'm showing here based on another study that suggests that there is an inverse correlation between how much the original construction budget is exceeded with the investment that an owner puts in the site investigation program. So that is, the more we invest in a good site investigation program, the less potential there is that there are going to be problems during construction. So this is not discussing about earthquakes, but this slide is. So adding the earthquake component, earthquake-related ground risks. They are often really controlling. For you who practice in seismic active areas, you'll know that in these areas, these types of risks often dominate the risk profile of projects, and they can control even project feasibility, not mention costs. And it is our duty as geoprofessionals in the earthquake engineering community to help our clients best manage those earthquake-related ground risks. But what are these risks related to? And it's basically the uncertainties, and there are two types of uncertainties that I'm showing here. First, related to the variability in the ground conditions, so uncertainty with respect to how do ground conditions vary. Think of it stratigraphy, but also properties. And here, let's distinguish between the inherent variability of the ground medium and then the uncertainty which is associated due to our limited ability to sample it and characterize it, so due to limited data. And then there is another type of uncertainty which has to do with how will the ground and asset respond to loads, and here I'm going to focus on earthquake loads. And these uncertainties are primarily related to limitations in our engineering tools, either the simplified methods or the modeling limitations, the tools that we have that do not have the ability to fully model and capture the response of a complex soil structure interaction system. And so I propose that we can help our clients best manage earthquake-related ground risks, but first trying to adequately characterize the inherent variability in the ground medium, and then, as much as possible on projects, try to reduce the remaining uncertainties. And if we do that, we have essentially higher confidence in our design. In a risk-based framework, this higher confidence translates in a better confidence on the distribution of the decision variable, of the outcome, which is what an owner uses to make decisions for their projects. So now, looking at the state of practice for seismic design, I think it has come a long way, at least for the past decade or a bit more that I have been practicing, from more prescriptive approaches to performance-based design. Here I'm showing an example from the Canadian Highway Bridge Design Code that specifies multiple hazard levels, and there are performance objectives that are tied to each of these hazard levels. So one would do analysis for several hazard levels and calculate a response of a system. However, you would notice that for seismic design typically, and this is coming from the same code, that a geotechnical engineer would typically use a characteristic geotechnical parameter, which is defined as a cautious estimate of the mean value. And this definition is not very accurate, or there is subjectivity there. It appears that there is an attempt to cover for the uncertainty, for some uncertainty there, but not by not very defining or quantifying what cautious mean. But we also know that cautious mean value, this is not uniquely defined, right? What is cautious for stiffness may not be cautious for strength. So this is a limitation in performance-based design in seismic engineering. Also, there are a couple of other things to note. These are approaches that are set in a pseudo-probabilistic framework, where essentially a system is modeled with a set of mean-like parameters, or parameters that approximate, a mean-like value. And they are conditioned on a return period for the earthquake loads. But this does not provide a distribution on the outcome. It does not provide a distribution on the decision variable that an owner may need to make decisions. And taking this argument a bit further, for highly nonlinear systems, for brittle systems, the return period of the decision variable may not be the same as the return period of the input earthquake. So there may be a mismatch for some projects, for some systems. There are frameworks that are more rigorous to account or calculate risk more rigorously, incorporating uncertainty and variabilities, inherent variabilities, in a rigorous analytical manner, using a series of fragility curves to correlate input motions to output and all the way to a decision variable. And with these approaches, you can calculate a hazard curve for what matters, which is the ultimate decision variable. And this hazard curve can give one the center, the body, and the range of the distribution of that outcome, which is not true for pseudo-probabilistic approaches that we're currently used to. So with that as a background for the motivation for the talk, I'd like to, and I know I didn't present an outline, these were my introductory slides. I would like then to take this opportunity to present two projects. And in these two projects, there are some common threads. The owner was not able to make decisions for how to move forward because either of the uncertainty in the geotechnical conditions or the complex system. And in these cases, we adopted a risk-based framework to quantify and calculate risk to enable the owner to make informative decisions to move forward. So these two projects are case studies from the San Francisco Bay Area, where I live and I mostly practice. One of the projects is what Stephen talked about, but is actually a much later phase of that project. So the first is the Port of San Francisco Seawall Resilience Program. One phase of this is called the multi-hazard risk assessment. And here we adopted a risk-based approach for decision-making to help the owner prioritize funds for improvement projects. The second is the Bay Area Rapid Transit BART, Offshore Transbay Tube Seismic Retrofit Design Project. This is an immersed tube that connects the cities of San Francisco and Oakland under the bay. And this is a retrofit design project, and you're going to see again we used a risk-based framework to help the owner make decisions with respect to the scope and the extent of the retrofit of this tube. So looking at these projects and the seismic setting, both are linear infrastructure projects, approximately 5 kilometers long. To the left, the Port of San Francisco, the seawall is the main feature. I'm going to talk about in detail in the next slides. It essentially marks the northeast edge of the San Francisco Peninsula. To the right is the immersed tube, which connects the cities of Oakland and San Francisco. And here, these projects are within 15 kilometers of two major faults in the area, the Hayward Fault, which is capable of approximately magnitude 7.3 characteristic earthquake, and the San Andreas, which is capable of approximately magnitude 8 earthquake. So this is unlike Vancouver, where you may have different types of seismic sources. We're in active, shallow tectonic margins, and we have well-defined strike-slip faults that control the hazard. These faults produced earthquakes, large earthquakes in the recent past. The San Andreas fault was responsible for the 1906 earthquake. It was a magnitude 7.9. It is known, you may have heard it as the Great Fire in San Francisco, because many utilities broke and there was devastation caused because of fires primarily rather than ground shaking, although there was damage indeed from ground shaking. And then there was a more recent earthquake in 1989, a 6.9 Loma Prieta earthquake. But this was 80 kilometers, again produced on the San Andreas Fault, but 80 kilometers south of San Francisco. So the intensity of shaking, or the shaking levels, were relatively low, although still we saw ground failures in that earthquake. Hayward Fault hasn't resulted in a strong earthquake since 1868. So this is the one that we're really expecting to go next. And USGS gives a 72% probability of a magnitude larger than 6.7 occurring in the area before 2043. So quite high probability. So let's look at this location here where the two projects, the two alignments intersect. And this is a pretty picture of where BART transitions from offshore to onshore under the landmark ferry building in the Port of San Francisco and continuing in the city of San Francisco. So what is the ground motion? What are the ground motions estimated at that location? I'm showing to the left spectra on bedrock for 3 return periods, starting from the 43 years all the way to 975. And if we look at 975, peak ground accelerations are around 0.45, 0.46 Gs. This is quite high, with similar acceleration levels at 1 second. And you see on the deaggregation plot to the right, this hazard is primarily dominated by events 7 to 8, between distances 10 to 20 kilometers, and these are earthquakes on the Hayward and the San Andreas Fault. So for one of the two projects, the multi-hazard risk assessment included 4 levels of earthquake, which were selected to capture a range from weaker, more frequent events to occasional, rare, very rare events for the 975. And so this is what we performed analysis on. Peak ground accelerations, again, around 0.1 G for the 43-year event, 0.46 approximately for the 975. So now let's look at the first project. Official name, Port of San Francisco Seawall Resilience Program. There is a lot of information on the web, and I have added here the link if you care to find out more. This is a port project, although it's not a port with modern standards. It was a port when it was first built, but now really it is the economic center and the touristic center of the Bay Area. And at the heart of this study is the seawall, which defines the transition from land to water. And it's essentially the foundation of the city of San Francisco, of the waterfront in this part. And so the area around of the seawall, which is referred to as the waterfront, I don't know, probably many of you know, you have been there, you have visited. It's a very vibrant area, right adjacent to the bay. There are a lot of popular attractions and baseball stadium, cruise ship terminals, markets, promenades, the iconic ferry building. It attracts more than 24 million people per year. There are lots of businesses, restaurants, but also disaster response facilities for evacuation during a potential disaster, transportation networks, utilities. So there is a lot going on, and this area is really the economic backbone of San Francisco with more than 100 billion in assets. Now, the Embarcadero seawall, which you see here in the plan view in the blue, with the blue line, is the foundation of the waterfront, as I said, and it was built more than 100 years ago, reclaiming land from the bay. You see also there some pictures of how before the seawall was built. And looking here at the cross-section, the seawall was built by excavating first a trench in the native soils, which in this case we have what is called Young Bay mud. It is a soft to firm marine clay. Then rock was placed to create this pyramid-shaped dike, which was capped with a concrete wall approximately 3 meters high, although this construction is not the same along the entire length. And then this provided the foundation for pier-supported bulkhead wharfs, and then buildings, pile-supported bulkhead works, and then buildings that were built on those wharfs. To the land of the seawall, the area was filled with heterogeneous fill that was essentially dumped into place, so we'll see it is liquefiable and quite heterogeneous. So what was and again, all this system was built around 1900s, so without the understanding of today's understanding of the high elevated seismic hazard in the area and, of course, today's seismic standards. So what was the owner, the Port of San Francisco, concerned about? The first hazard was earthquake-related. So the possibility that during strong shaking, the liquefiable fill will lose strength, spread horizontally towards the bay. The Young Bay mud beneath the seawall would also soften up, start to slide towards the bay. This would disrupt the piles, which would break, would damage the wharf, and then that would create damage to the buildings. On the land side, you also see that there would be cracks on the highway, the Embarcadero highway, and the evacuation route towards the sea would be disrupted. So such a response, or a potential response, apart from being very threatening to life safety, creates also has the potential to create significant economic damages. The second hazard, which I'm not going to talk about today, is related to coastal flood, but this was addressed by the same study, the multi-hazard risk assessment. This is why multi-hazard, earthquake and flood. But what I'd like to point out was that the timelines of the two hazards are not similar. So earthquake is more urgent, more immediate, and coastal flood, primarily associated to sea level rise, is a bit longer term. But the port, recognizing both hazards, embarked on a program back in 2017, the Waterfront Resilience Program, to essentially create a sustainable and resilient waterfront, and part of which is the Embarcadero Seawall Program, which I'm going to talk about today. And this is a 10-year program with a goal to strengthen for earthquake and protect from flood, and plan to adapt and envision for longer term. So the port, recognizing the high variability of the conditions, and we'll see the geotechnical conditions are quite variable, but also the complexity of the different structures, they asked for a risk assessment study. So they were the ones who requested that this study be performed to help them prioritize the investment of their spending, of their funds on retrofit projects. So this project was won by a team which was led by CH2M Hill and Arcadis. They were the program manager. Fugro is the lead geotechnical engineer. I'm in the role of the lead geotechnical engineer. SGH is the lead coastal and structural engineer in this study. And this team implemented the risk framework that the port requested to essentially help the port guide their investment, guide the port's investment decision. And there are three building blocks in this type of framework. The first is to define the hazards. So in this case, the earthquake. The second is evaluate essentially the vulnerability to these hazards, identifying the consequences, and then combine those two components to assess the risk. And the risk here was assessed in terms of variables that addressed both casualties, so life safety, but also economic variables, direct damages, downtime, and such economic variables. So there was a big team, a lot of reports were produced, but I'd like to, from now on, focus really on the geotechnical aspects of the study. Before I do, briefly talk about past earthquakes. So this area has been shaken by, two large earthquakes in the recent past. So some of this infrastructure has experienced these earthquakes. So I'm showing some pictures from damage during 1906, where piers collapsed. Both from the 1906 earthquake and 1989 Loma Prieta earthquake. In both earthquakes, areas of field land experienced ground failures. So in 1906, displacement, settlements, but horizontal spreading was on the order of maybe half to a meter. For Loma Prieta, it was lower, maybe 5 to 10 centimeters order of magnitude from studies that have been published. So we know something about past performance, and this is something that these are observations that can be used for us to calibrate against when we're doing forward studies. So previously I said that essentially uncertainties in geotechnical parameters and in system response parameters control the risk profiles of projects in highly seismically active areas. So for this particular case, how do these apply? So to the left, we're looking at how do ground conditions vary. I'm showing a geotechnical cross-section. This is a conceptual section. It was put together, was prepared based on a desktop study, an overview of the geology of the area before we did our project-specific site investigation program. And we do see that conditions are expected to be variable. We have variability with respect to the thickness of key layers, such as the Yang Bay mud, that are responsible for the seawall stability, variability with respect to depth to the rock, but you also see these yellow lenses, and these turn out to be sand lenses that are liquefiable and can further compromise seawall stability. So our approach was with a project-specific site investigation plan to characterize this variability in the ground conditions to the best of our ability within the constraints of the project, and essentially maximize the information that we got from the geotechnical data. When we're looking at the response of the system, this is a relatively complex system, so it wouldn't be very well represented by simplified methods, say like the Bray and Travassaru, as much as I would like to. So here we opted to adopt more advanced numerical tools to better represent the complex soil structure interaction and increase the confidence in the mean response. So don't panic here. This is not the site investigation program that we proposed for this project. These were the data that the owner had at their hands when we started our exploration from other projects in the city, but they had those data. So we reviewed them with the purpose to identify whether they were relevant, we could use them for our study, and for quality. And so you can see here that we, let's see. Let's see if I'm better using this. Maybe. Okay. So here we use the ranking system. So essentially, we screened over 600 borings and explorations to rank them and evaluate whether they could be used in our study. Essentially, we determined that for the most part, we could use them to delineate stratigraphy maybe some of the CPTs for property measurement, but it was primarily, these studies were used with few exceptions, or these explorations to delineate the stratigraphy around the seawall. Now, we developed a project-specific site investigation plan to be able to obtain relevant data to evaluate seawall stability. And here we really thought about the goals and the objectives, so we want to be very purposeful about delineate the goals and objectives of this plan in order to really maximize the information extracted from each of the exploration. And so we identified goals as, for example, here listed in terms of priority, characterization of young bay mud strength and stiffness, and then more detailed objectives within that goal. Another goal was essentially to characterize the seawall, the composition and its foundation material, because it was unknown. The owner thought that it could be liquefiable, the seawall itself. So maybe we had sands rather than bigger rock fragments. Another goal was to characterize the liquefaction susceptibility and the properties of the field behind the seawall. And then we had secondary goals. And these goals guided the types of explorations that we chose to perform. So we had 4 different types, I think 5 of explorations between borings and sampling. We did cone penetration tests, field veins for strength measurements, and sonic borings to get a better characterization of the dike. And also similar thinking went into developing an adequate laboratory testing program. So all in all, we ended up with new recommended explorations, 89 explorations, 5 different types, and these were spaced. It was in the immediate vicinity of the wall, such that they're more relevant for the seawall stability, spaced such that we can get the variability along the length of the seawall. But here an interesting concept was that we planted what we're calling couples of explorations. So for example, the CPTs and vein in situ vein couples, or triplets, CPT veins and a boring, such that we can get measurements of the same parameter, for example, undrained shear strength, from 3 different types of tests, and develop project-specific calibrations. These then would increase our confidence in our measurements, would have the potential of reducing the uncertainty in the measurement, but also we could use the more less disruptive, more economical CPT, which is shown here with the green, to characterize a bigger part of the waterfront, again, considering budget and time constraints. These are some pictures from the exploration program. It was one of the best sites to work at. It almost felt like vacation being out there. And it was executed smoothly. It was well thought out, and the fact that we gave a lot of weight in those areas where we had the couples and triplets of explorations, and then we went with many CPTs. This really helped, as you're going to see. So this is a reinterpreted subsurface cross-section going past the conceptual, where I'm focusing here in Yerba Buena Cove, which is the area where we have the thicker young bay mud, approximately 30 meters of young bay mud. Apologies here, this project in the US, we're working on with imperial units, but I'm trying to do the conversion and talk in meters. So approximately 30 meters of young bay mud in this area. And again, you see all these explorations were not new explorations, but the CPTs, most of the CPTs were ours. And you see that the CPTs identified, here I'm showing this cross-section. So this was a 3-dimensional model. I'm cutting 3 sections that are shown here with the blue. And what is shown here is the cross-section bay side of the seawall, so the marine cross-section, if you will. And what you see here is that the CPTs picked up this silty sand layer that we're referring to as young bay mud sand, because it occurred like sheets, interbeds within the young bay mud. And it ended up being critical to the seawall stability because it ended up being liquefiable. But let's first look at the characterization of the Yang Bay mud. So one of the most important parameters for the seawall stability is the strength of this material, which is now the foundation of the dike. So here I'm showing a cross-section in one part of the seawall. You're seeing the dike here. And I want to present results for these exploration triplets. So one is here in land, and there is another triplet bay side of the wall, where we performed in situ veins, CPTs, and then a laboratory test. Before we tested in the lab, we x-rayed every tube, so we were sure that we had good quality samples. And to the right, you see some results comparing in these two locations these three sets of tests. So the CPTs, the field veins, which were very frequently run every 1.5 meters to essentially get a nearly continuous profile of strength with depth, and results from strength tests. These were monotonic, direct, simple, undrained, direct, simple shear tests. And here we see really excellent comparison between these three sets of data. And this comparison held for all the couples and triplets along the seawall. We used one single NK factor to calibrate the CPT along the entire length of the seawall. So this type of data really increased our confidence and reduced the uncertainty in the strength parameter of the Yang Bay mud that was used for modeling. Then we performed one of the key elements of the response was the cyclic response. So we did stress-controlled direct simple shear tests and strain-controlled tests to characterize cyclic strengths, to characterize the evolution of the shear strain with a number of loads. And here we're also concerned about post-cyclic strength degradation. So we did also a series of tests where we recentered the specimen after it was cycled and then pushed monotonically to look at the post-cyclic monotonic strength. And these results, so we developed quite an extensive data set that was then used to calibrate the input for the numerical models. So when we're looking at the sand, here's where, again, the CPTs and the CPT couples with borings came in very handy. So the CPTs were very successful in delineating the thickness and the extent of this layer along the seawall. But then we used borings with targeted sampling for classification, and we were able to develop project-specific correlations of the fines for the fines content CPT with lab tests. We also did plasticity. We ran Atterberg limits. So all in all, we used the CPT to classify the material based on I sub C. This material was primarily silty, sandy, but based on the plasticity, in the end, in our simulations, we characterize it as a sand-like behavior. So it did really affect wall stability. So with that, on the characterization, let's go on to how does the system respond to earthquake loads, so uncertainty in the system response. So here we performed two-dimensional analysis with FLAC. For the fields and the liquefiable sand, we use PM4 sand from Boulanger's Geotechnical, but also UBC sand as an alternative model to account for epistemic uncertainty. For the Yang Bay mud, PM4 silt with an alternative UBC hist by Dr. Nasgard. And then, despite the fact that we had 2D analysis, we did model piles with springs, so we did model pinning effects from the wharfs and the piers wherever applicable. So before we use this analysis to trust them and advise the client with respect to the level of deformations for the different level of earthquakes, we want to have confidence that they can indeed replicate observed performance. So the first step is to calibrate the input parameters, again, either project-specific tests, which we did here, or available tests in the literature. So again, here we focused for PM4 silt and UBC hist. We focused at behaviors like at capturing the small strain stiffness and stiffness degradation with shear strain, modulus reduction, and damping. But more importantly, as I said before, the cyclic strength and the potential for large shear strain accumulation. And we had alternative models that we used in our analysis. For liquefaction, obviously focused on triggering, but more importantly, the post-liquefaction shear strain accumulation, which we're also referring to as compliance rate. And once we have, so another thing to say about the calibration of the constitutive models, and having done a lot of work in this area, it's very difficult with one set of parameters to capture all behaviors that would be applicable, right, for a soil medium. So here what we want to do is focus on the key behaviors that are relevant for our system and make sure that we're not off in other responses. And here we really focused our calibration on strength and cyclic strength and also post-liquefaction shear strain accumulation, also making sure that we were not off in the wave propagation, in the propagation of seismic waves. And so with an appropriate calibration, going on to a validation at the system level, and here again, we were looking, this is looking at the ability of the numerical model to represent key physical phenomena that are relevant for our system. So here we analyzed experiments that are available in the literature. For example, a clay embankment, looking at slope instability, looking at the calibration approaches for the same model with different input parameters, and what is the approach that gets us closer to the observed response. We participated in the liquefaction experiment and analysis project, LEAP, and performed extensive comparisons against centrifuge experiments modeling lateral spreading. We analyzed centrifuge experiments looking at site response analysis with very good comparisons between observed response here with the black and computed response of surface spectra. And we also analyzed the 1906 earthquake and the Loma Prieta earthquake. Of course, for 1906, we did not have recordings. We used simulations. And we compared the estimates of displacements, approximately 2 feet, so 60 centimeters. This was on the order of magnitude of what was reported in the literature. So these analyses more than passed the reasonableness check. So we felt that we had a tool that we could use confidently to estimate system response. So here I'm showing results from our analysis for 4 cross-sections that have vary with respect to the conditions, the types of foundations of the dike and the thickness. To the bottom left, we're looking at thin Young Bay mud. Here is where we see localized deformations. We see rotation of the concrete wall. Where we have this Young Bay mud sand layer, we see very localized deformation that can be very disruptive to piles. To the right, where we have thicker Young Bay mud, we see more distributed deformations. And here in this case, we don't have softer Young Bay mud under the dike, so we have very little deformations. So all in all, the thickness of the Young Bay mud and the presence of Young Bay mud sand and its thickness affected the amplitude of deformation and the deformation patterns. We analyzed many different cross-sections along the waterfront, and these are what I'm calling spaghetti plots, the horizontal residual displacement at different locations along the cross-section. But looking at the displacements of the center line of the dike, these are ranges that we are coming up with, and these are for mean of 11 ground motions. So for the 43-year earthquake, relatively small displacement, 3 to 10 centimeters. For 100 years, 15 to 30. 2 to 5, this is where we start getting to larger deformations, especially in areas like this to the north of the waterfront, where we have bigger thicknesses of this young clay mud sand beneath the dike. And for 975, getting to very large deformations. So now these results, we did some, we developed a methodology to be able to interpolate for other locations, and we're able to develop contours that were also used for the risk assessment of buildings on land. But this is the types of input that was used by the structural engineer to develop the fragilities. So the structural engineer was looking at more than 100 different structures along the waterfront based on different construction methods and different materials. They grouped them in 17 groups, and they developed fragility curves as a function of 5 different damage states, which were defined in quite a bit of detail. And then these fragility curves were used in a risk analysis, which is based on a HASUS approach, where we're estimating economic losses, direct damages, and other losses, but also casualties. Please don't focus on the numbers. I don't mean to show the actual numbers, but just the framework. These types of results then were used by the port to select early projects to move to the design and the construction phase. So now the port has identified 11 projects that are shown here with the blue that they are prioritizing based on this risk assessment. They are advancing to, and we are now supporting them. We're continuing on the next phase, which includes essentially developing of retrofit alternatives and up to 15% design. So with that, wrapping up this project, what was it from the geotechnical perspective that made a difference, that helped the port make good decisions and prioritize their investments? 2 things. One to the left related to how the ground conditions vary. We planned our site investigation very judiciously, with very clear goals and objectives in mind, with a goal to really maximize the information that was extracted from each of the exploration. And this helped increase the confidence and reduce the uncertainty in some key parameters that were governing the seawall stability. And to the right, we increased the confidence in the engineering analysis by selecting the right level of modeling, not more than that, not less than that. So avoiding oversimplifications, which tend to increase uncertainty, but also avoid over-analysis, which may have been or may be more appropriate when you're going into final design. So with that, I'm going to switch gears and go to the second project, which is the immersed tube tunnel, BART offshore transbay tube seismic retrofit. It connects, again, San Francisco to Oakland under the bay. And the tube was built back in the 60s when there was limited knowledge of the elevated seismic hazard in the area. And it was built in a trench, which was excavated again in native soils. It was filled with liquefiable sands. And the tube segments were essentially lowered and placed and connected in that trench. And these tube segments were 100-meter long segments. So when Fugro, back in 2006, I started with Fugro when we were still working on the proposal for this project, and we were hired to essentially develop a ground mitigation scheme to prevent the tube from uplifting during strong shaking, because the tube is nearly buoyant, and it was perceived that liquefaction-induced uplift was a key vulnerability. We worked on this problem for 2 or 3 years. We did extensive modeling, including centrifuge tests. We put the liquefaction-induced uplift into rest, proposed appropriate retrofits, but through these studies, we identified other areas of vulnerability. As you see here, we're looking at a longitudinal cross-section, and so you see to the west, near the middle, and to the east, there are areas of sloping ground, and in these areas, there are slope-induced vulnerabilities that are very relevant and that the owner was not initially aware. For this project and for the uplift problem, we had pushed couples of CPTs very close to the tube, within 1.5 meters of the tube, to characterize the relative density of the trench fills. And these CPTs are going to come in handy for this study, the most recent study that I will discuss in this presentation, because they also characterize a small part of the tube trench. So for this project, the owner had project-specific criteria, seismic criteria, 2 levels of earthquake, the 1,000-year return period, the performance was essentially safe egress, so evacuate people from the tube safely. That was the key performance objective, not saving the tube. And safe egress relates to how quickly the tube can fill if it ruptures during an earthquake. So it relates to water inflow. And there was a lower performance criterion for the 500-year return period, a lower hazard level, but don't want to get into specific performance criteria there. How we started analyzing the system was the same concept: use mean-like or deterministic properties and sensitivity analysis to see whether we had a brittle system. And account for some uncertainty in the properties. But we see that we're only able to do so much with this approach. So we had to adopt a different approach. So again, this is a plan view. These are pretty pictures of numerical models in the different areas. I'm going to focus in zone 3, but here we also did some 3-dimensional analysis. Focusing now in what I'm calling zone 3, which is the area of slope instability behind Yerba Buena Island, where there is a scour hole. The vulnerability assessment there included the following type of analysis. We were responsible for the geotechnical evaluations to come up with kinematic demands on the tube due to slope instability, transient and residual. These were input into a global analysis that was run by another company, Structural SE Solutions, which were essentially estimating or computing the axial strains in the tube. And these strains were input into more detailed models, structural finite element models, to estimate cracking in the tube shell and then water inflow. And based on these results, back in 2018, where we did the first analysis of this system, we came up with a retrofit strategy that the owner adopted. And this consisted of having a structural shell internally to provide more strength, but also create an impermeable shell from inside the tube. And so construction started, and as I said in the beginning, they had problems during construction. The costs were escalating significantly. There were significant delays. At the same time, there were changes in earthquake science and also in the engineering tools. New models were coming out, like PM4 silt, etc. So the owner, back in 2020, said they're going to stop construction and came back to Fugro's team. This was a team that was led by Fugro to perform reanalysis of the system. And the goal of this reanalysis was to right-size the scope and the extent of the retrofit. So did they have to retrofit the entire tube? How big of a length did they have to install this shell in? And so we started performing this analysis, and as you can appreciate here, this project started back in 2006. So it experienced multiple phases of exploration and analysis for different vulnerabilities, for different problems. So now we're going to run into a situation where even when we're purposeful about collecting data for the uplift problem, we find that we don't have enough data for the slope stability problem. So what do we do with that? So this is a plan view of the area to the south of Yerba Buena Island. We had, a long time ago, performed geophysics initially. This is an area where we're expecting to find this Yang Bay mud, and that would govern the stability. You see here with the contours, the focus on the scour hole. So we went and performed borings and in situ downhole veins, they're shown here with the circles, with a goal to characterize the strength of the Yang Bay mud and the properties of the Yang Bay mud. However, these borings revealed that there were some sands in the area. So during that same exploration program, that was back in 2009, we went and were able to squeeze in 2 CPTs with a goal to delineate thickness and primarily the properties, the relative density of the sand. Here you're also going to see that we have the old CPTs from where we were working on the uplift problem, and these were the CPT couples that are shown on either side of the tube with green. So with this information, we also build a 3-dimensional ground model. This is where we see the sort of slope coming in. And for the purpose of this presentation and this analysis, I will look at the longitudinal cross-section where we have the biggest slope. So 3 longitudinal cross-sections, one through the tube center line to the north and to the south. And this is what they are looking like. The middle is through the tube center line. You barely see the tube here with the thin green lines. But what we notice is, for the most part, the trench is sitting on Yang Bay mud. But there are these 2 CPTs here that are picking sand, and the sand is loose. And there is also sand upslope of the tube. And if we're looking at those CPTs with depth, and the tip resistance is now converted to equivalent N160 clay sand, and we also look at the cumulative distribution with the thin lines, the color lines, we have each CPT separately. The thicker lines are different types of averages, distributions, but we see there is a big range. So what does one do with this range? What do we design for? Are we characterizing this layer with an N160 of 15 based on a mean? Are we trying to capture this distribution, and in what way? So looking at how this affected the slope instability, that, again, we performed numerical simulations. This is in the tube longitudinal direction, but here is the slope. This liquefiable sand, during strong shaking, develops excess pore pressures and tends to move downslope, dragging the tube with it. And depending on the properties of this sand, so for example, if we model the relative density or equivalent N160 with 15 or 20, the displacements are very different. More importantly, what I'm showing here is the differential, the peak relative displacement between any 2, between every 100 meters. So we're calling these the tube joints. And you see, if we're modeling the sand with N160 of 15, we have relatively big peak differential displacements that also extend quite a bit upslope. If it is with N160 of 20, the smaller displacement, and these have an effect on the axial strains. So this type of analysis developed time histories, displacement time histories that were used in finite element analysis in ADINA performed by the structural engineer to come up with the tube response in the axial direction. So with the pink here, you see the tensile strains, with the green compressive, and it's the tensile strains that cause cracking in the tube. And now if we see what does this mean for inflow? So if we model this layer with an N160 of 15, the distribution for all the 11 ground motions that were run is shown here with orange. So you have a mean that is probably around 7,000 gallons per minute in terms of inflow, but the median is very close to 2. So you have a very brittle system. If the sand is modeled with an N160 of 20, you have a much smaller inflow. So presented with this information, this is where we started working with the owner, and they really didn't know what to do. Should they design for these levels of inflows, this level of inflows? What should they do? And we said, okay, we don't have, the best thing is to cast this into a more rigorous probabilistic framework. At the same time, the structural engineer identified areas of uncertainty in the tube, like the parameters that would affect this response that they were uncertain about. So we went and adapted this framework that I previously discussed for this particular problem. And so we developed project-specific fragility curves. So starting from an intensity measure, we set the spectral acceleration, I think it was at 1 second. And as a function of stratigraphy and as a function of the relative density of this sand, came up with the demand parameter, which is the residual soil displacement. Then as a function of the residual soil displacement, which is, with the residual soil displacement as an input and as a function of soil springs that control the interaction between the soil and the tube, calculated strains through the modeling that SE Solutions did that I previously showed. And then with these strains as an input and as a function of the tube properties, we calculated cracking and inflow. So we came up with fragility curves to essentially model every step to go from the ground motion input and the return period all the way to water inflow in the tube. Not displacements, not strains in the tube, but really how fast water was coming in. And then this essentially relates to how fast you can evacuate people. So again, we developed a logic tree where the key areas of uncertainty was modeled as separate branches. Here we even modeled stratigraphy with some uncertainty. That was with respect to the extent of the Yang Bay mud sand, how far behind upslope of the tube did it extend. As I said, the relative density, the soil springs, which method do you use? Do you use, the method by Idris and Boulanger? Do you use the method by Kramer? There is quite a bit of uncertainty there that is usually, people don't incorporate in analysis. And then there were other parameters which were more related to the behavior of the steel and the concrete of the tube. But in the end, we developed hazard curves. So the annual frequency of exceedance of the inflow in this particular case. Here, each of these lines is one line, one analysis in the decision tree, and this is essentially the percentile. So you can appreciate there is approximately 1 order of magnitude difference between the inflow for the 16th percentile and the 84th percentile. But it was essentially this type of information which was cast in this, was presented in this way, that helped BART decide what was the scope and the extent of the new retrofit, which they're now implementing. So with that, in looking at a summary, what is our client's goal? I presented 2 projects where essentially our clients want to make decisions to meet some engineering objectives or objectives for their projects with limited resources, and they were unable to do so with the more conventional approaches that exist. The main challenge was essentially uncertainty in the ground conditions, inherent variability, but also uncertainty in how a complex system responds to earthquake loads. For these projects, and with different focus and to a different extent, the geotechnical approach was threefold. The first is that we looked at data collection with a very purposeful attitude, with the goal to maximize the uncertainty reduction given the constraint of the project. So we planned the explorations and the laboratory testing with the goal to extract the most information possible out of limited number of explorations and reduce the uncertainty as much as possible. That was for the Port of San Francisco project. We selected analysis tools with the appropriate level of detail, selected to capture the key behaviors of interest. And then we implemented a framework that allowed the client to evaluate the distribution of the key decision variable, but not that allowed them to make decisions. So with that, sort of lessons learned from these 2 projects, what can we do as geoprofessionals in the projects that we deal with day to day? And I would say call for action here. Be very purposeful about the goals and objectives of the site investigation and laboratory testing plan. Execute the right site investigation well. This is what my colleague and former supervisor Ray Wood likes to say in Fugro. Do not execute the right investigation wrongly, nor the wrong investigation well. So the right investigation well, it's important. Consider combining exploration types to maximize data value. Adopt analysis tools that represent the response of the geostructural system at the right level of detail and complexity for the purpose of each study. Calibrate such tools with a focus on key behaviors controlling the response and across a range of loads, which is important especially when you're looking at risk assessment, spanning a range of earthquake loads from weaker to stronger. And then be creative in developing an appropriate probabilistic framework to estimate the distribution of the metric of interest to the client, parenthesis decision variable, that allows them to act. And so without some acknowledgements, there is really no innovation or no ability, for a practitioner to sort of push the state of practice if there is not a receptive and open-minded client on the other end. So I'd like to thank Zakaria Samare and Mark Salmon of BART and Steve Reel from the Port of San Francisco for being exactly that. Nathan McCullough from Jacobs for being a very good partner. He was the program manager for Jacobs on the Port of San Francisco project. A peer review panel which supported and encouraged our approach and made some good suggestions along the way. My colleagues Ray Wood and Rod Edis that created a culture in Fugro to discuss and issues about ground risk, but how to manage ground risk. But more importantly, my colleagues Jose Ugalde, Alfredo Fernandez, and Adam Price, who are the brains and the hands behind implementing and delivering the approaches that I have presented today. And thank you for your attention.
Maybe we have time for just sort of 2 questions.
Regarding the site investigation, I wonder for samples to see what. Would you use geotechnical investigation or not? I know that that area is so noisy. Okay, I will repeat my question. Regarding the combination of the investigation and taking data for San Francisco seawall, I wonder if you use geotechnical investigation for getting parameters of the soil. I know that that area is so busy. Maybe the reason was that you were skipping.
That was exactly the reason. It is an extremely busy area, very difficult to do explorations. Actually, the reason why we did a few explorations, or as few as possible, was that we had to work at nights. I mean, some explorations were done at night. Now we're out there also doing some explorations at night. Geophysics, we did downhole geophysics, but not if you're thinking of reflection, refraction, or maybe W. Because of the difficulties and the challenges, it was going to be very time-consuming and very difficult. Also, we wanted to get information within the vicinity of the seawall. We knew more or less, the conditions. As I said, there were tons of boring. So we're really after properties and conditions really around the seawall. So we're very, very, the targets and objectives were very specific, and they were not very well serviced by geophysical investigation.
Thank you. And the second one, I wonder for lab testing, I think you have already measured damping. Did you check the damping curve versus shear strength with what we have usually? I know that the damping measurement is very difficult.
And I don't have this slide in this presentation on purpose. But no, I know exactly what you're talking about. One thing that was working on our favor in this study, of course, right, the damping from the constitutive models is higher, although we try to reduce it as much as possible at large strains. The thing that is happening here is that the key behavior is ratcheting. So you never really have a full curved loop with big hysteresis. What you see is essentially that the wall is ratcheting its way towards the bay, and so dumping becomes secondary. And this goes back to what I was saying before. I think you need to be understand what you're what is important for what you're trying to calculate. Focus your calibration there, and probably leave with weaknesses, right? Or it's impossible to cover everything. But in this case, it was not really a controlling parameter, I should say. But definitely within much, the dumping curve.
Thank you very much.
Thank you. I think we'll have to hold the questions for the coffee break or afterwards, but I'm sure I'll be around.
Okay. Thanks.
Thank you very much.
Thanks a lot.
All right, so now we're going to give the VGS Award. So for those that don't know, the Vancouver Geotechnical Society Award is bestowed each year to a member of the local community who has provided essential service, been an influence, and been a trendsetter in the community. So to give this year's award, I would like to invite Susan Tattersfield to the stage.
Hello everyone. I'm excited to have the opportunity today to announce that my manager and mentor, Karen Savage, is the recipient of this year's VGS Award. I have had the pleasure to know Karen for over 12 years, both professionally and personally. I recall first being introduced to Karen through a family friend in 2011 when she kindly took me out for lunch during her busy work day and answered my lengthy list of questions about the practice of geotechnical engineering, which greatly motivated me to pursue this career path. When Karen decided to form her own geotechnical consulting company in 1997, she was an early adopter of ensuring a corporate culture that allowed individuals to have a balanced family and work life, when many engineering consulting companies at that time did not have such foresight or willingness to make such changes or commitments. Karen wanted to ensure a workplace that allowed employees to also be able to raise a family while balancing a professional career. Through hard work and dedication to such beliefs and principles, Karen admirably balanced her roles as a professional consulting engineer, successful business entrepreneur, highly active volunteer to various engineering association committees, mentor and role model for myself and numerous other young engineers, and a wife and mother who volunteered her time in her children's classrooms and helped to develop science curriculums for young children where there were none previously. As a professional engineer, Karen actively contributes her time and efforts to help improve the profession of engineering by serving roles for EGBC, the Association of Consulting Engineering Companies, EGBC Foundation, and Engineers Canada, where she currently serves as the Canadian Engineering Qualification Board, where she currently serves as on the Canadian Engineering Qualifications Board for Engineers Canada. It was during her role as chair of the EGBC Professional Practice Committee that she was instrumental in updating EGBC's geotechnical guidelines for building projects, thereby raising the standard of our profession and better protecting the public. Karen has been a leader by example for promoting workplace equality, especially for women in engineering. She has been an invited participant in the Prime Minister's Task Force on Women Entrepreneurs and an invited delegate on multiple occasions for Engineers Canada Task Force on developing and implementing gender equality policy, which helps to break down the glass ceiling for myself and other female engineers. Karen has, as a part of her continuing efforts to help improve the overall engineering practice and construction industry, She has been the primary author of several publications, including BC's Housing, Foundations, and Geotechnical Challenges in BC, and their Builder Guide for Site and Foundation Drainage. In 1998, Karen received the Professional Service Award from EGBC. In 2008, she was recognized as a Fellow by Engineers Canada. In 2002, she received the Meritorious Achievement Award from the BC branch of the Association of Consulting Engineering Companies and the Dean's Medal of Distinction from UBC's Department of Applied Science. In 2003, Karen was elected as a Fellow of the Canadian Academy of Engineering. Karen has mentored myself and numerous other young engineers and students with continued eagerness and encouragement to help them gain experience and opportunities for professional and personal growth. As a consulting engineer, Karen's expertise is in high demand by both private and public sectors. Karen's ability to communicate complex problems and solutions to a wide field of audience in conjunction with her extensive knowledge and engineering experiences make her a sought-after subject matter expert. She strongly promotes continual improvement to raise the minimum quality of geotechnical engineering so that the public safety is protected and the profession will not become stagnant. By literally leading by example, she has noticeably made a difference in both the engineering profession and the regulations that govern this profession. Congratulations, Karen, for your award, and thank you so much for your continued mentorship and support.
This is a tremendous honor. I would like to express my deep appreciation to the VGS executive for this award and for finding me to be a worthy recipient, particularly when I cast my eyes on the list of greats, including some of my past professors who preceded me. We all know that engineering is a team effort, and I will thank my team. However, at this time, I would particularly like to single out my colleague Takahiro Shozen for his excellent analytical skills, practicable construction solutions, and wise counsel. He has patiently taught me much, and I've relied heavily on him over the last 21 years to keep me out of trouble. I would also like to thank my business partner, Kareem Zadigan, who joined Horizon in 1999, for keeping me level, for the laughter, and for our Friday Scotch o'clock. To me, the most important questions to ask in geotechnical engineering are, where's the water? What's it doing? And what was it doing 10,000 years ago when our geology was being laid down? Thanks to Robert Ing for all the fun we have had over the last 22 years of geofantasizing about our geology, which is what we call developing a geologic model. But I think geofantasizing is often what we do. I would like to recognize the love, encouragement, and support that my husband, Ben Vandersar, gave to me when I started Horizon Engineering in 1997, and the support, encouragement, and love that our children continue to give us. And I thank two of my kids who came earlier, which we thought we were getting this earlier, but they had to go back to work. So it is known that stiffness attracts loads. And looking back at my accomplishments, I do believe I have demonstrated strength. We all also know how important lateral confinement is in order to avoid buckling. Of late, there have been more lateral loads in my life, so I am forever grateful to be surrounded by wonderful colleagues who give me that lateral support, especially those here today from Horizon Engineering, and who have been there to more than simply support me. Lyndon Chen, Nima Tapsoli, Diane Meehan, Jason Tam, Ulysses Ye, Ali Rostami, Haroon Bucks, our esteemed speaker from this morning, Susan Tattersfield, Jason Young, Rain Thompson, and welcome to Karandeep Kular, Shobi Sivapalan, and Hassan Pashnazez. At Horizon, we strive to be right, reasonable, rigorous, reviewed, responsive, and respectful of when we do our engineering. And I'm really proud of the excellent engineering that we do together and would not be up here today without my team at Horizon. Thank you.
Thank you, Susan, and thank you, Karen. So for our next speaker, I would like to invite Arantha Raja and Daniel LeBond, who will be co-presenting.